So up first we have John Mount. He's going to talk about data algebra, but before we go into the talks, let me talk about how this is going to work. We have our timer here, Jay. Jay, we're going to give everybody 6 minutes because we only had 6 people sign up. We have time to do that. And then I'm going to completely abuse my role as moderator to take the last spot of 6 minutes. Then, so John's going to speak for 6. Jay's going to count him down. When he gets to here, this is 30 seconds left. When he gets to here, this is time. And I want everybody, when you see Jay's fist in the air, everybody should start applauding. That is your, yes. Then it is like the Oscars. You are being played off the stage. And you need to get off so that the next person can come on, because I only want to have 1 minute between each time. I have ambitions. So John is going to start first. He's got 6 minutes. And then up next, we'll have, is Leland McInnes here? Leland will go next. All right? To you. Start time.
Thank you. My name's John Mount, and I want to talk about something really quickly that we're developing at our group, WinVector, called the data algebra. And it's kind of in the count your fingers after you shake its hand stage, so it's an early phase project. But it's something we've used a lot and we're kind of proud of. So quick outline, what is the data algebra? Work a horrific example, where we are with this project, and some links. Basically, the links are easy. Look for WinVector blog. We'll put up all the slides. So you don't need to write anything down. We'll post this tonight. So what is the data algebra? It's a package for building up complex data queries. It's basically a lot like dplyr if you're from the R world. And it's basically, the idea is, what if we made queries, data queries like transformations, adding an extra column to a data set, selecting a subset of rows of a data set, joining two data sets, summarizing a data set, or appending in a summary. What if we made those first order operations that we say stacking these operations is important? The data is an irrelevancy that we'll enter into later. And how did I pick that set of operations? Well, I'm running through Codd's relational algebra, what he considered the important data operations. And I think that's sort of an uncelebrated backbone of a lot of our data processing, even in the NoSQL or non-SQL worlds, is that small set of operations that Codd selected, essentially joining, unioning, selecting, appending rows, appending summaries. He missed window functions, but we'll put those back in. I think those are basically the things that are important. So the operators in the algebra are those. Composition, we write left to right. The data starts on the left and moves through the operators to the right. So we don't get this weird sequelism where composition is built by ugly nesting, that a query is deep inside other queries. And actually, I kind of lied there. I don't compose over the data. What enters in is the description of the data. And the idea is, because a description enters in, now let's be a live room. What's a classic Codd description of data? A schema. So basically, data algebra takes in a schema and produces a set of operations that produces a resulting schema. And we can compose data algebra operations if the schemas match. So basically, if you're saying simply y equals x plus 1, is there an x column present? And that's what lets us treat the queries as first-class citizens, things we can keep around for a long time and reuse. Because again, when we're doing data science, we always apply all the operations to our training data and then later to our test or application data. So we never ever want to do the operations just once. And the idea is, since the representation is pretty neutral, it can execute directly on pandas, or it can later emit SQL. And that's all implemented. And we're basically playing with Modin and Rapids and others, but we haven't really got that part working yet. But this is what the data algebra looks like, and this is the total meat of the talk, that the blurry top thing is a pandas data frame. Then the blurry next line after that is a table description is describe that table. All it does is says, I'm a table that has columns G, X, and V, essentially schematizes it. Now, once we have that schema, we say an operation is a table description piped into an extend node, piped into, I'm saying pipe, but what we're doing is method chaining. When I say pipe, I mean that dot backslash. And what comes back is a query representation, table descriptions, a query representation. Each and every one of these is a larger query representation. And the extend is what Codd would have named adding a column. Or it is what he named adding a column. And what we're saying is that order by the variable x and partition by g. So we're basically doing a window function that we're going to add in per group summaries into the original data frame. It skips having to build a summary data frame and then joining. And then the next one is an extend that has a partition but no order constraint. And then it just builds this table. It takes this real tiny table that only had G, X, and V, and it builds this table that has the other columns, such as lagged variables, per group summaries. Per group summaries is my absolute favorite in data science, because how do you know whether you're big or large relative to your group? Well, the easiest way would be if somebody would land your group mean as a column, and then you just compute the difference. So data algebra, everything is written into these tiny little steps, but they're very easy to reason about. And then at the end, you expose it to data using the transform method. Or if you don't want to expose it to data, you say emit SQL, and then it would emit the horrifically large SQL that this represents. So where are we? The code works well enough that we're using it for internal projects. We also use its R siblings, rQuery and RQ data table, which are also our product, WinVector LLC, on our internal projects. We haven't inflicted it on that many users yet, and we've had to completely avoid it in our new book, Practical Data Science in R, because we don't want to teach anybody something weird. You don't want to wrap up people for failure. And we're looking to extend it to other things, beyond SQL, beyond pandas, maybe Modin, maybe Rapids, things like that. So here are the links. So basically, everything can be found by just knowing my group's name is WinVector. The project's on GitHub. It's available through PyPy. We have an introduction to it here. And we're building up that it has a nice category theoretical interpretation. And let's do the fist. Thank you.
I'm glad that the extra minute seems to be helping people out get to the end of their talks. So Leland is up. Next, we're going to have Anne-Marie Fulser.
Topic modeling is to model a corpus of documents in terms of some sort of underlying topics that describe the documents. All right, so I'm just going to turn all of that into matrix factorization really, really quickly. So the goal of matrix factorization, I've got a big matrix of data. That might be a bag of words model of a document where it's just counts of how many times each word, which are your features, occur in each document, which are your rows, and I'm going to represent that as two smaller matrices multiplied together as closely as possible. That's matrix factorization. So we've got the data. The red section there is your low-dimensional representation of the data, and the green stuff is the archetypes, which in our case would be the topics. So what we're really saying is that a row or a document is represented as this representation times the archetypes. So in other words, we're describing that as a linear combination of these topics. So a document is a linear combination of topics, and that's really all we're doing. So that's topic modeling as matrix factorization very quickly. So linear, latent Dirichlet allocation and PLSA are a couple of probabilistic matrix factorization methods that are common ways to do this. Well, latent Dirichlet allocation is the common way to do this. PLSA is the less common one that I'm going to use and explain. Okay, what I want to do is ensembles of PLSA. We'll get there in a minute, though. So first of all, why am I using PLSA? Performance. So I wrote an implementation of PLSA using Number to get really fast performance out of it, and the result of that is that using the scikit-learn latent Dirichlet allocation or non-negative matrix factorization, I can do this particular corpus in 2 minutes with LDA, about 3 minutes with non-negative matrix factorization, or 16 seconds with PLSA. All right, so I'm probably just cheating, right? Because I did something very fast and it's garbage. But it turns out that if you measure the results, it actually performs better at modeling these documents than either NMF or LDA. So PLSA is a good way to go, but it's unstable. So what the problem here is that these are hard optimization problems. We're solving a probabilistic matrix factorization, and topics vary from one run to another. You run it twice, you get a completely different set of topics, and now no one trusts the topics you produce because you never get the same thing twice. How do we fix that? Well, the goal is to find the stable topics. What we can do is run it a whole lot of times, generate a whole lot of topics from a whole lot of different runs, embed them with an embedding technique, cluster them with a clustering algorithm, and then you're getting just the topics that recur a lot under lots of runs popping out as your clusters. You find the centroids of those clusters, or basically average those topics in multinomial parameter space. That's where the topics live. And the end result of that is you get out a representative of each topic, of each stable topic. So Each cluster there is representing a stable topic, and as you can see from this quick measure of whether this is doing a good job or not, it does actually do a good job of boosting your performance. So what are you getting out of this? Well, you have greater stability. You run this multiple times, you tend to get pretty much the same topics out every time. They're not identical, but they're very similar. It dramatically determines the number of topics automatically for you. LDA, you normally hand it how many topics you want, and it gives you exactly that number. This, you give it a ballpark number, and because it's using clustering to find the number of topics, it'll give you more or less than that number, but it's whatever number actually occurs in the documents. And this is all embarrassingly parallel to run the computation because we're just simply running a whole big ensemble of these. So, implementation. I have written an implementation of exactly this approach. It has an sklearn API, so you can use it right now. It's on GitHub. Here's where to find it, on GitHub. I'll give you a second for that one in case you want to write that down, or just pip install nstop and it'll work. You can try it right now. Thank you.
Wow. All right, I was pretty fast. I feel better. All right, Anne-Marie, you're up next.
Hi. Yeah, so my name's Anne-Marie Fulser. I'm a UX researcher at Microsoft. This will probably be a really quick talk because I didn't realize that this was like a presentation thing. But I just wanted to talk to you guys about what I do and how I'm here to help you. So like I said, my role is a UX researcher. I'm not a data scientist, but my role is to talk to people and try to make your lives easier. So that consists of I do interviews, I do surveys, I try to see how you guys interact with products and where things are missing or where they could be better for you. So I'm not a data scientist, I don't have something really cool to show you, but I just kind of wanted to communicate to you that if you guys have anything you want to share with me, I really do just want to make your lives easier, even if you don't use Microsoft products. My job is to understand you guys, what you guys are doing, where you guys are heading, and how that could all be better for you. You may have noticed the little whiteboard that I have outside with a bunch of different magnets and icons. That's just a fun way of how I do research, and I hope to engage with all of you and maybe connect with you later. Yeah, like I said, quick talk. I was not expecting this. Thank you guys.
Excellent. If this keeps going this fast, I'm going to get to talk really a lot at the end. You all are going to love it. It's going to be amazing. So, Caitlin, you're up. Matt Seal.
Okay, so my name is Caitlin Wilkinson, and I'm a designer at Microsoft, and I work on the developer tools design team. I work with Anne-Marie and Jeffrey on the Python extension for VS Code, and for the past 4 or 5 months, we've been really focusing on a new native Jupyter experience inside of VS Code. When I joined this team about 6 to 7 months ago, we didn't think it was possible to have a native Jupyter view inside of VS Code, and this is kind of what it looked like. So you had a Python file on one side and then your output on the other, and we had all of these crazy usability problems with our customers, people were getting lost in their file, no one knew what to do or how to use the product at all. And then in about July, we realized that we could do a native Jupyter experience, and in October, we released this. So now that we can have native Jupyter support inside of VS Code, so basically what we've done is made our own UI inside of VS Code to go in and load a notebook for you and display everything in line just like you would for a regular Jupyter notebook experience. But the funny thing about this was that we couldn't use any of the controls available to us in VS Code. We had to build everything from scratch, and we had to work with about 2 other teams to make sure that we were creating a cohesive experience with other Microsoft products. Kind of like what Anne-Marie was saying earlier, we've been doing lots of research, talking to a bunch of people. It doesn't matter if you're using our products or not. We just want to know how you do what you do. And that's been a main thing for us. And so we're pretty new. It's a pretty new part of our tool, and we have a long ways to go, but check it out. We're pretty excited about it. Yeah, that's about it.
Very cool. Nobody's having to get applauded off the stage. I'm really deeply impressed with everybody's discipline. I don't have that, so Up where we have Matt, and then we have the last lightning speaker who signed up, Chris Ariza. Perfect.
All right, we're going to do the cardinal sin of presentations and do some live coding. All right, my name is Matthew Seal, and do I have the wrong thing in? Oh, no, you can't see my screen. I'm going to talk about Scrapbook. Scrapbook is a little library that I pulled out of Papermill back a year or so ago. And it hasn't got a lot of love in the past 6 months for me, but now I'm back, so I'm working on it again. And I'm going to show you what it does and why it was made. All right, so we're going to start with the inability to click on my browser tab. Oh, no. No, I can't open anything. All right, one sec. All right, Scrapbook is a project which lets you, I will show you what the code would do. And if I can get it running, then I will. I'm so sorry. All right, so Scrapbook lets you do this import. You can basically save data. So it adds the ability to programmatically save and recall data from notebooks. So if you think of notebooks as kind of a function, the outcome is always a notebook. You can't ask for the data that came out of the notebook. So Scrapbook lets you save the data by using this glue function, and you can glue data into a notebook. And then yeah, we take the metaphor a little far. And then down here you have, you can even put images, which if this were running right now, which it's not, you can render the images and save them at the same time. And then in the result reader, which I cleared conveniently so I could show how it ran before, this, you can recall the code here. So you can read the notebook, and then you can get all the things that were saved in it and go reiterate them. So I can print out what the data was for that list argument that I saved, which would be a list of 1, 2, 3. And then I can get the actual data, not as text or as a JSON blob. And then I can also grab the image back out, and I can call this .reglue, which saves the image back into the notebook. So I can go fetch an image. I can save images as outcomes and then recall them and collect them in some other place. And then the cool thing in the experimental branch, which I was going to show you, is in the experimental branch, you can support pandas directly. So you can save pandas data frames and then recall them, and it'll bring them back through saving them as base 64 arrow. And then the other thing you get is it'll have support for saving the data in S3 instead of in the notebook document. So you can save a reference to your data in S3 and recall that reference. And then I had a great little part down here that showed that I pulled the list from S3 and that the list was over here. Actually, I can show you what's saved in S3. So I got this dict. See how I saved it in S3? That was what I had in my notebook when I said store this in S3 and put it into my user directory over here. So if you want later, after I unplug this HDMI cable and kill Chrome, I'll show you how it actually runs. So thank you. Oh, very also, cool. Contributors welcome. It's open project. There aren't a lot of contributors yet, so.
Very cool. I actually want that to work because I need that for my life. I'm not kidding. I'm serious. Like the ability to export like a graph and a pandas thing and then show that to a product manager, delicious. So last we have Chris Ariza.
Great. Hi, my name is Chris Ariza, and I'll be talking to you today about the best defense is not a defensive copy. So I do a lot of work in table-based processing systems, and as part of my work, I review a lot of code by my colleagues where they are working extensively in pandas. And what I observe often is a fear of unintentional mutation leading to defensive copying. So what is there to fear? Well, pandas objects are mutable in place. Values can be mutated or reordered in place. Indices can be reassigned or mutated in place. Making defensive copies of pandas objects is a common solution. So what's wrong with defensive copies? Well, they're expensive in terms of both time and space, and can result in less predictable performance depending on what code paths happen to work through your code. So some fear is warranted. Side effects lead to bugs. It is well known that, for example, a function that mutates its arguments can lead to some very bad behaviors. If the argument is reused downstream, functions will get a changed result. A class that has mutable attributes that were intended to be read-only, if a client mutates those attributes, different clients are going to get different results, and that can cause really hard to understand bugs. So we'll look at two examples of code extracted from my colleagues. I've simplified and extracted them here, where we see this fear of mutation leading to defensive copies. So in this example, we have a function that is we see this function called processor, which is taking functions, which is an iterable of functions, and those functions are being called in a loop, and each time they're being called, they're given this dictionary of previous results, called results here. And as you can see, the results are being copied every time they're put into this function. And my colleague took this approach because he was concerned a naive user writing one of these functions would mutate the arguments, and understanding the negative consequences of that, copied the entire bundle of inputs every time this thing loops around, which, as you can imagine, is very expensive. Another example is a case where a colleague was creating a class that was to serve as interface to data. Here I've created something very simple and lightweight, but the data stored in the real case was much bigger, where the data is created at initialization, and then some properties are made available to retrieve those data. As you can see here, the property is copying the data every time the attribute is accessed. So a naive user of this class may just think they can use this property, but every time they're using it, they're actually getting a copy out. And as you can imagine, this can be very expensive. So what's better than defensive copies? Well, we can make arrays immutable. And there's two approaches we can do that. So one approach is to simply use NumPy instead of pandas when we need immutability. And we can do this because NumPy arrays implement the buffer protocol as defined in PEP 3118, which dates back to 2006. There we see, and in NumPy we see that the NumPy array has a flags and a writable attribute that permits making arrays immutable. So let's look at an example. If we create a NumPy array of integers, here we create an array of 10 integers, typically with a NumPy array we can mutate a value. Here I assign -3 to index 4, and as you can see the array is mutated. But I can tweak the flags. Looking at the flags, you can see all the flags available, and I can simply set the flags.writable to false. And now the array is immutable. You can try to assign there and you'll get a convenient error. This is a good defensive move. However, using NumPy alone is challenging, as you all know. There are no labeled axes, automatic alignment of data on labels doesn't happen, there isn't good missing value handling, which leads one to consider if only there was a pandas-like tool that managed immutable NumPy arrays. And there is. It's called Static Frame. Static Frame is an immutable alternative to pandas. It has many similar features with more strict and consistent interface, and what it does is automatically manage immutable NumPy arrays. So for example, in Static Frame we can create a series. It's very much like a pandas series. And here I'm creating a series of 5 values with a character index. So in Static Frame we can try to assign to a position in this series. And we'll get an exception, and we'll say, well, this object doesn't support item assignment. Well, many of you know, well, that's just easy. I can just work around that. I'll just go to the underlying array, and I'll mutate the array. But yet, if you try to do this, again, we find an exception. The array has been made read-only. So Static Frame has been in development for over 2 years. It's deployed and actively used at research affiliates. And we're looking for feedback. We're looking for features, questions, and PRs. You can find us on GitHub. You can pip install it. It's ready to go right now. And we'd love to hear from you. Thank you.